let's try to see if we can use model checking. Okay? Why? Well, there is a lot of work on optimizing model checking. Model checking is really going well. Okay? People are using that industrially quite a lot. So, well-developed thing. What about if we can use it, okay, to scale this to bigger systems? And the answer is yes, you can do it, but you cannot model check any transition system. You have to model check something that is slightly different from a transition system, that is a game structure. And this is what I want to look at now. I'll go back there. So these game structures are really a beautiful thing because completely easy and trivial, but extremely powerful. So let's look at them. Very nice. So first of all, we know essentially that given a transition system, we are able to compute temporal property on this transition system. How? By computing Mu calculus formula, by computing fixed points over these transition systems. Okay. By the way, Mu calculus is also the most expressive temporal logic that you can think of, but it's also the one that is used in practice. So most of these systems are actually computing temporal property by executing essentially the evaluation required by the Mu calculus formula. Okay, so we have this Mu calculus. On the one end, is a very nice formalism, very general. On the other end, its construct corresponds to actual computation that you can do on the model, and they are used in the mainstream model checker. So we want to use this idea, exactly the same idea, except that we cannot really do it on a transition system, because we don't have a transition system here. Why? Because in a transition system, all the decisions about what to execute next, okay, are decided by the single agent that is executing a transition system. Okay? So maybe this agent is composed from several agents that all together execute the transition system, but you are quantifying essentially over each transition in the same way. Instead, here we want to consider that there are two players going around. One player is a sort of enemy who will try to make the composition fail. And the other player is a sort of good guy who will try to actually realize the composition. Okay? So at each point, what we want to be able to distinguish if now is going to be executed the bad guy or the good guy. Okay? And the idea is that on the bad guy we cannot do anything, so it's uncontrollable, it will do whatever it wants. So we will quantify universally over the bad guy. Instead, the good guy, it's us. We are deciding what to do there. So we quantify existentially on the good guy. Okay? And we are going to alternate for all exists, at each point in time. Okay? For all the moves of the bad guy, I'll do a good move. Okay? The good guy will do a good move. Okay? So the bad guy is called the environment, and the good guy is called the controller. Okay? The bad guy is in red. Okay? And how does this game structure work from a formal point of view? Well, actually, it's a transition system. It's really a transition system. However, in this transition system, you partition, okay, the states in what can be controlled by the environment and what can be controlled by the controller. In particular, what you normally do something like this. You take a set of variables that are controlled, so assume that these are a set of variables that can assume only a finite, that have a finite codomain, okay? They can assume only a finite number of values, okay? And of all the variables of the system, you consider x as the variable controlled by the environment and y as the variable controlled by the controller. initially they will all start in a certain configuration. Okay? Then the environment will do a move. And how it does a move? Well, you look at the current state of its variable, you look at the current state of the controller variable, and it will generate a new move. Okay? New assignment for the variable it can control. Okay, this is the transition of the environment. And then we have a transition of the controller. The transition of the controller, what it does? It looks at the old value of the variable of the environment, the old value of the variable of the controller, the new variable for the environment, okay, because it looks at the new move of the environment, and then it decides the new assignment for the variable of the controller. So it works like this. We start from a certain state. The environment will move first and will decide the next value for its variable. Then the controller will move, it will look at this new set of variable and will decide the new assignment for the variable of the controller. And this will go on forever. Okay, so this is how the transition system is built. Go ahead.
It's not deterministic, yeah?
Non-deterministic, absolutely. Everything non-deterministic. Okay, and then I told you we're going to do, so this now is a structure, okay, it's perfectly defined structure. Okay, it's very similar to a transition system, but I now distinguish two kinds of transitions, okay, the one from the environment and the one from the controller. And what it means that I distinguish them, I have a way of distinguishing them. I now can quantify over these transitions in a different way. And that's exactly what this variant of Mu calculus does. Okay, so this is the usual Mu calculus. I don't have time to get into it. Okay, but there's only one thing that is very important. Is this green stuff over here. So the green stuff says the following. Next V is going to be true. Okay? But what do you mean next? Next after a transition of both the environment and the controller. And actually, the interpretation, the right interpretation is the controller can force phi to be true next, can force phi to be true next. Okay? So it's not going to be true. It will make a decision such that this is going to be true, in spite of the decision of the environment. So this is the actual definition. Okay? So it means, what this says is, next it means that the environment can do a move. Obviously, we want this thing to move always. And for every move that the environment can do, observe, for all moves, there exists a move of the controller such that phi is true next. This is the key point. This property is a very nice feature. It's local. It's not looking at anything that is going to happen later. It's just looking at what's true now and what's going to be true next. Completely local. Okay, so maybe it's not the most easy way of computing next, but the computation is actually completely local. So it will not affect any of the computational property of the Mu calculus. That's the point. And so, what it means that we can actually do computation, Mu calculus computation over this game structure, okay, exactly with the same efficiency that we can do Mu calculus computation on a transition system. And now, let's play a little bit with them. What about service composition? How can you write service composition as a two-way, as a two-player game structure? Well, what you have to do, you have to decide what are the variables of the environment and what are the variables of the controller. Okay? Who is the controller here? The controller is the orchestrator. Okay? And the environment, all the rest. So the target is working against you, against the orchestrator. The available services are work also against the orchestrator. Everybody is working against the orchestrator. Okay? The orchestrator, the only thing he can do, he can choose who's going to do the next move. Okay? But then, which is the move? Who's going to which transition the selected service will do? This is all environment, all things that you cannot control. Okay, so in spite of them, you want to be able to do the composition. And so you see, essentially, the state of all the guys, of all the service are in the environment. The action selected is in the environment. There is also some bookkeeping thing, error, that is in the environment. We keep error just to say that at this moment, the target has to do something, but the controller, the selected service of the controller by the controller could not do it. Okay, so you raise a flag. Okay, if service says one has to do it, but one cannot do it, then you raise a flag and say error. Okay.
Same state or?
And then once you give an error here, you say in the same state it is not important anymore. If you have an error, the composition is not valid, so you should stop. Okay, so here it does the most stupid thing you could do when you get error. It's here essentially when error is true. This should be when error is true.
At the end,
nothing happens. Okay, so if error is true, nothing happens. And then you can produce error true if you cannot actually simulate the target at that particular moment with that particular choice. Okay? And this is what we want as the formula. We want to maintain forever that we are not in error. Okay, forever, so it's a maintenance goal. Not in error, and forever. Every time that the target is in a final state, also all the services are in a final state. Okay, and you compute this. Is by the way, greatest fixed point formula. Okay, it essentially says that this must be true always, forever. By the way, it's easy also to write planning domains using two-game structure. Okay, here, for example, it's a planning domain in which I think there are exogenous events. No, sorry, not exogenous events. In which what happens is this: the controller chooses the action, and the environment chooses the transition that it does with the action, so the value assignment to the transition. Okay, and then the eventually goal, eventually a certain thing is true, is a least fixed point formula over the goal is true now or next, the same thing will be true. So the goal will be true now or next, the same thing will be true. This might happen a final number of times because it's a least fixed point. And by the way, you can say very strange things like, I don't know, the goal eventually, for example, it's always true that I can reach the goal, okay? Not only now. I reach the goal now, but then again I'll be able to reach the goal, and then again I'll be able to reach the goal. So these are fairness constraints. All of this easy to write. Complexity, I mean, it's good. So it's the same complexity of Mukaros. Essentially says that it's polynomial in the size of the structure and the size of the formula. Polynomial or what? Actually, there is a difficulty here, and it's the alternation of the fixed points. Okay, so if you have a greatest fixed point and least fixed point, this will actually increase the complexity. Okay, so you have to count the number of alternations.